So to continue on with alpha carbons, here we are in the conjugate addition reactions. And what can we do? What does that mean? We've shown the formation of the aldol condensation where we make the alpha beta unsaturated aldehyde or ketone in there, and we can show resonance structures for this alpha beta unsaturated carbonyl where we send in the first resonance structure break the carbonyl, sending the electrons to the oxygen, making it negative, and the carbon positive. And then we can also show where the double bond chases the positive, and we get this with the positive on the beta carbon. So in this alpha beta unsaturated carbonyl, it is reactive towards a nucleophile, or a nucleophile is reacted towards it at either the carbonyl carbon or the beta carbon, because that's where we can draw a positive charge in our resonance structures. So if we add a Grignard, and the Grignard or the alkyl lithium, so RMGBr or RLI, the Grignard or the alkyl lithium are the only things that really add 1,2. And 1,2 is where the nucleophile adds to the carbonyl, sending the electrons up, and then you put the hydrogen on there. Everything else, all other nucleophiles, add 1,4, where they add to this carbon here, the beta carbon, sending the electrons through on up to the carbonyl, and then you draw a resonance structure and put a hydrogen on, and you end up with the carbonyl back. So the 1,2 destroys the carbonyl and gives you just a carbon-oxygen single bond. The 1,4 addition reforms the carbonyl in the reaction. Okay, and those are the two things we can do to the alpha beta unsaturated carbon. So we have the nucleophile, it adds to the beta carbon, sending the electrons all the way up on the oxygen. We form the enolate. We can put a hydrogen on the enolate in acid to make the enol. And then from the enol, we'll just redraw it again down here, we can keto-enol tautomerization, where we send the electrons down, it goes out and grabs a hydrogen off of the acidic water to give us, keep dropping my hydrogen, the hydrogen, we get the nucleophile here. And then in the last step, water can remove the extra hydrogen off of the aldehyde, protonated aldehyde, to give us the neutral compound. And we get that. Okay, that's the 1,4 addition. So, can we draw some Michael donors, weak bases, because of resonance structures? Okay, they're going to be all sorts of things with negative charges on them that are resonance stabilized, and Michael acceptors are all going to be something where we have an alpha beta unsaturated carbonyl of some sort. So as we're going, we'll talk about these and fill them in as we're going along with this. So in the first one here, the single ketone isn't as good of a Michael donor because it's much more acidic. The hydrogen on there is much more acidic. The base is a lot stronger, so it doesn't work as well as the 1,3-dicarbonyl does. So the 1,3-dicarbonyl is a good Michael donor because it has the resonance stabilized portion in that. So in that, it doesn't work as well, so we can't use cyclohexanone pull off a hydrogen and add it to methyl vinyl ketone to form this in good yield. Okay, but we could use the 1,3 dicarbonyl and it would work in good yield. But what we can do to help it work is to take a little bit of acid and a secondary amine, and we can make the enamine. We've drawn this mechanism before. The enamine, we can show a resonance structure where we have the negative on the alpha carbon, the double bond to the nitrogen, with a positive up there. So the alpha carbon of the enamine is very nucleophilic, so it can do things that we couldn't do previously. So we can draw resonance structures of the enamine as we just did, comparing it to the enol the enolate that we have below. Okay, they both end up being very similar in how they can react. Okay, the enamine is more stable, so it's a little easier to deal with having the having the alpha carbon be a nucleophile. So we can show what would happen in this. Where we're going to get O minus this. This is going to be our intermediate in there somewhere. And then when we add acid and water to that, it's going to give us something that looks... We're going to cleave the iminium ion back to the ketone and draw the resonance structure and protonate the alpha carbon of the other one, and we get that out of the two steps. So the enamine is a much better way to do it than the enolate, just because of the stability of it. So what can we do with these types of reactions? We can do both the alpha carbon and the 1,4 addition reactions by starting with a Michael donor and a Michael acceptor and doing a Michael reaction, Michael addition in that. So it's an addition to the beta carbon of the alpha beta unsaturated carbonyl. It makes this, and then we can do an aldol condensation. So we can do everything in one reaction in this Robinson ring annulation. That's kind of a cool reaction in what we can do in that one pot. And we'll draw a mech of it in a little bit. So what can we do for synthetic strategies? We can take an aldehyde and we can make the aldol addition, or the aldol condensation. If we make the alpha beta unsaturated carbonyl, we can take a ketone and make the Claisen condensation. They both produce a 1,3 difunctionalized compound, so it gives us a lot more things to work with on this. In the Stork enamine synthesis, we end up where methyl vinyl ketone, we'll draw it out again, methyl on one side, vinyl on the other, we form this bond. It gives us a 1,5 difunctionalized compound, so it gives us another spot that we can put something on in there. And depending on what we need to do, we can do other things also. So with the alpha beta unsaturated carbonyl, we said that Grignards and alkyl lithiums add 1,2. They add to the carbonyl. They give you the alcohol. They are the only two things that add 1,2. Everything else adds 1,4. So the diethyl cuprate here is just a copper with two ethyl groups on it with a negative charge with the lithium as the counter ion. It is going to add in an ethyl group on the beta carbon because it is being the nucleophile. So it's going to add the ethyl group in, send the electrons up to the oxygen, So we make the enolate, and then in the simplest of terms, that enolate could go react with methyl iodide to alkylate the alpha carbon. So we can alkylate both the beta carbon and then the alpha carbon stepwise by what we do in the reaction. Gives us a lot of control over what we can do and a lot of added functionality. Right. So if we had a problem, we have going from this allylic alcohol to the alcohol shown, so going from compound A to compound B, how can we do that? Right. We know we have to form a carbon-carbon bond, so there aren't a lot of ways we can do that because we change the carbon skeleton. We add 2 methyls on. So what reactions have we covered? We've covered oxidations back in the first test, alcohols, made ketones and aldehydes. We've covered Michael reactions where we can add something onto the beta carbon of the carbonyl, and we've done alkylations on the alpha carbon of this. So when we look at this, we have to form a bond to a methyl off of the beta carbon, put a little red dot there, and a methyl on the alpha carbon, a little purple dot there. So how can we do that? We need to oxidize our alcohol up to the aldehyde, so PCC. Once we have the alpha beta unsaturated carbonyl, we can add the dimethyl cuprate. That'll add to the beta carbon, so that'll put the methyl on that carbon. Oops, I should have made that the red dot. That'll give us the methyl on the red dot, okay? And then after we do that, we add the methyl iodide, and that'll put the methyl on the alpha carbon, the purple dot. And then from there, we can take our alcohol or our aldehyde, and we can reduce it with sodium borohydride in methanol, and we'll end up with the primary alcohol of reducing the aldehyde down to the alcohol. Okay. So in this reaction, it takes 4 steps to do this multi-step synthesis. Don't try to condense them down and do everything all at once. Spread them out. Think about stepwise, what reactions have we done? Okay. And try to keep it as simple as possible as you're going along.